So, all right. This is part 4. Sorry, part 5. I said part 5. Part 4 of our notes. So we did first our periodic table review, and then we've done our periodic trends, and then we did the electron configurations, and now we're going to finish it up with our electromagnetic spectrum. Okay, so in the quantum mechanical model. So again, remember, our test is going to be next Tuesday and Wednesday, so y'all's will be on Wednesday. And your classwork and your homework will both be due that day. So just make sure you're taking care of business accordingly. All right. I will remind you that test is all going to be multiple choice. It'll be the last test of the 6 weeks, and there'll be 50 questions on it. Okay. So, all right. So let's get started. Right. Electromagnetic radiation, or the electromagnetic spectrum. A lot of people abbreviate this as EMR or EMS. Okay, so you need to know that it's really just a series of energy waves, and I do want you to know the actual order of those energy waves. So the electromagnetic spectrum, or the electromagnetic radiation, is a series of energy waves. That's what you first need to write. Now, those energy waves go in a specific order, so I want you to write those energy waves down. I want you to write them in this order. I want you to write radio waves, microwaves, infrared, visible light, ultraviolet, also known as UV, X-rays, and gamma rays. And really the only difference is right here, that I want infrared before visible light. So again, those are radio waves, microwaves, infrared, visible light, ultraviolet, X-rays, and gamma rays. So the way that I remember that is with the acronym or the saying, red Martians invaded Vegas using X-ray guns. Okay, so the red would be for radio waves. The Martians would be for microwaves. Invaded would be for infrared. Vegas would be for visible light, because in Vegas there's lots of light. Using would be for UV. X-ray would be X-ray. And guns would be for gamma rays. So red Martians invaded Vegas using X-ray guns. All right. That's the way I always remember the electromagnetic spectrum order. And the reason that you need to understand the order is because for the electromagnetic spectrum, as you go from radio waves to gamma rays, so this is written backwards from what I just said, but as you go from radio waves to gamma rays, the wavelengths actually get smaller. So I do want you to write that down. As you go from radio waves to gamma rays, the wavelengths get smaller. In this picture, it has it the opposite direction, has it from gamma rays to radio waves, and it has the wavelengths getting bigger. So your biggest waves are going to be your radio waves. Your smallest waves are going to be your gamma rays. All right. So let me grab my annotation because I want you to write something else as well. I am writing with my mouse, so this might not be as pretty. Okay, so the wavelengths decrease as you go from radio to gamma. But as you go from radio to gamma, there's something also called frequency, which I'm going to draw as an F. That's really bad. And the frequency goes up. Okay. So as you go from radio to gamma, the wavelengths go down, but the frequency goes up. That's going to be a key thing here later as we're going along. Okay. So, all right. Again, from the radio waves then would be the lowest frequency and the highest or longest wavelengths. Gamma rays would be the highest frequency, but the lowest wavelengths, or the smallest wavelengths. Okay. All right. Hopefully everybody's still doing good. And we've all got the information written down. All right. So like I said, we can measure not only the length of each of the waves of light, but we can also measure its frequency of occurrence. So if this was a second of time, this wave would actually have 4 cycles in that 1 second. Whereas this wave right here is smaller. Okay, it's more scrunched together. So it would happen more often, and it actually happens 8 times in this 1 second. This one's even more scrunched together, so it would happen 16 times in this 1 second. The key thing to realize here is that is frequency. Frequency is how often it happens. So as we go down this picture, the frequency goes up, okay? But notice as the frequency goes up, the wavelength went down because the wavelengths got smaller, all right? So parts of a wave, I need you to draw this on your paper. Okay, so you just need to draw a middle line here. And that's really like our equilibrium or origin line. And then this blue line is your wave. And it goes up and down and up and down, a lot like a water wave. Okay. Now the very top of the wave right here, these are known as crests because as they go above the origin line, it's known as a crest, the very top of it. Then this right here is known as the trough because it's going below the origin line. From crest to crest is a wavelength. I could also have said it was from trough to trough. That would have been a wavelength also. I could have also said a complete crest and a complete trough. So a wavelength is just a complete cycle of a wave. And then the amplitude is really the height of the wave from the origin. And we're going to write these definitions down in a minute. But I do want you to just understand the picture. So the amplitude can be drawn from here, from the origin to up to the crest. It could also have been drawn from the origin down to the trough. So really it's just the height of the wave, how much it moves off of the origin line. So you should have 4 things labeled on this wave. You should have the crest at the top, the trough at the bottom, the amplitude as the height, and the wavelength from crest to crest. Are we all good with the picture? All right. Again, and this is just the origin line. All right. All right. So let's go with the parts of a wave. So let's go with these definitions. All right. And these are going to be important as we move along. So again, the amplitude is just the height of the wave from the origin to the crest. It also could be from the origin to the trough. So I really always just write the height of the wave from the origin. Okay. Then wavelength. Wavelength has a symbol. The symbol is going to be important later on. Wavelength is going to be a lambda. This is really like an upside down Y. Okay. It's a Greek letter, all right? And it is the distance between the crests. It could also be the distance between the troughs, or it could just be, like I said, a complete cycle of a wave. Now, since it's a distance, we will measure it in meters, just to let you know. Now, frequency is going to have the variable V on most of the things that I've printed for you already. But I will tell you later on in these notes, you're sometimes going to see it as an F. That's because when I use it in physics, I do it as an F, so that's what comes most natural to me. But any actual chemistry textbook, for some reason, uses it as a V, so I'm not really sure why. There's a difference between the chemistry subject area and the physics subject area, but I just wanted you to be aware that you'll see it both ways. But most of the time, the variable that you'll see is V, but you may see it as F2, so I want to make sure that you know that. It is the number of wave cycles to pass a given point in a certain amount of time. It's really a rate. I will just tell you that. It's the rate that waves pass a spot. All right. Now, the units of frequency are real important. It's 1 over a second, which could also be written as seconds to the -1. Or it could be written as hertz. So since this test is going to be multiple choice, I could say, which of the following is not a unit for hertz, or not a unit for frequency? And I could list all these different units, and then like I might put something like just seconds. Well, if I put just seconds, seconds isn't a unit for frequency. Okay, it's either 1 over a second, seconds to the -1, which is the same thing, or hertz, which is also the same thing as these other two. So all of these would be units for frequency, but just seconds would not be a unit for frequency. Okay. So again, amplitude's height, wavelength has the symbol of a lambda, and it's the distance between crests. Frequency will have the variable either F or V, and it's the number of wave cycles or the number of cycles that pass a given point in a certain amount of time. Its units are 1 over a second, seconds to the -1, or hertz. All right. So finding frequency, this is going to be one of the two formulas in this section that we are going to do. So here's where I said frequency right here is listed as an F. So I have it as F equals C divided by lambda. So that's one way to look at this formula. Let me write it another way for you as well. Okay, you could also look at this formula as C equals F times V, or excuse me, F times lambda. All right. You could also look at this formula as lambda equals C divided by F. Now remember, everywhere I've written an F, you could also have a V instead. Okay. Now, in this formula, C equals the speed of light. And the speed of light is 3 times 10 to the 8th meters per second. That means that anything actually on the electromagnetic spectrum, no matter whether it's visible light like yellow light or red light that we can see, or if it's gamma rays or radio waves, doesn't matter which one it is, all of them travel at 3 times 10 to the 8th meters per second. All of them do. That's a really, really important key thing to make sure you know. This number will be given to you on the test, but again, and it's given to you on your classwork, and it's given to you on your homework, but what you need to understand is all light travels at this speed. Okay, F in this formula is frequency, and like I said, it's measured in hertz. Lambda is the wavelength, and it's measured in meters. Now, this statement right here on this screen really needs to be written on everybody's notes, needs to be bubbled, starred, whatever, okay? As the wavelength goes up, the frequency goes down. And that's because if you remember, with this formula right here, this format, if this F value, okay, goes down, then this wavelength has to go up to keep the speed the same. And if you remember on the very first picture that I showed you, I told you that radio waves and gamma rays, that as you went from radio to gamma, the wavelengths got smaller. And if the wavelengths got smaller, then the frequencies had to get bigger. So they always had to be inverses of each other. They had to do the opposites. And that's because we always have to keep this speed the same. Okay? So as the wavelength goes up, the frequency goes down. That's a big, big concept to make sure you understand. And the reason for that is because we have to keep the speed the same. All right. Oh, I have to erase my little drawing. Sorry. All right. So let's do an example problem. Okay. So a certain wavelength of yellow light has a frequency of 2.73 times 10 to the 16th seconds to the negative 1. Calculate its wavelength. So we're given the frequency value as 2.73 times 10 to the 16th seconds to the negative 1. This number has 3 significant digits in it. This is the only number we're given, so our answer, remember, will also have to have 3 significant digits in it. All right. Now we know that because it's yellow light, it travels at 3 times 10 to the 8th meters per second. So we're trying to find the lambda. That's what we're looking for. Okay. So using our formula of F equals C divided by lambda, which can be rearranged, like I told you, of lambda equals C divided by F. And there is a division sign there. It's just really light. Okay. So I can do lambda equals C divided by F. Well, I know the C, which is 3 times 10 to the 8th. And I know the frequency, which is 2 times 10 to the 2.73 times 10 to the 16th. So grab your calculators. Everybody needs to do this in their calculator because we need to remember not to use the times 10 and the caret button. Okay. So when we type this in the calculator, everybody should type 3, and then they should hit the EE button, which is next to the letter A. And on your screen, a little E will show up. Remember that E means times 10. Okay. So then we're going to type the number 8. And then we're going to divide. So hit the divide sign. And then we're going to hit 2.73. Then we're going to hit the EE button again. And then we're going to hit 16. Then we're going to hit the enter button. Now you should end up with a number that is 1.0989 e to the negative 8. If you didn't get that, double check with your neighbors. See if they can look at it. Again, I'll remind you to make sure that you're doing the division. Make sure that you did 3 and then the EE button to the 8, and make sure that you divided by 2.73 and then did the EE to the 16. Okay. Now we need to round that number to 3 significant digits. So when we round that number to 3 significant digits, it comes out to be 1.10 because the 098 rounds up to the 0.10. And then we have times 10 to the negative 8 because that E stands for times 10. And we have negative 8 meters. Okay, since it's wavelength, we're in meters. Hopefully everybody's good with that calculation. All right, so let's talk specifically about the visible spectrum. On the electromagnetic spectrum, the visible spectrum is the only part that we can actually see, okay? We can't see radio waves or microwaves or infrared rays, UV rays, X-rays, or gamma rays, but we can see this, okay? The way to remember the order of the visible spectrum is Roy G. Biv, okay? So Roy G. Biv needs to be written on your paper, and that's for red, orange, yellow, green, blue, indigo, and violet. Okay, that's the order of the electromagnetic spectrum's visible spectrum. Now, really, these are just the colors that are produced when white light, which is what sunlight is separated by a prism. Okay, when you separate the light, it'll actually separate into all of its colors through a prism. All right. The thing to realize here is that red is the longest wavelength, but the lowest frequency. Okay. Red is closest to radio waves, so that makes it longest. Okay. They're the biggest wavelengths. Violet, on the other hand, is closer to ultraviolet or gamma rays, so it's the shorter wavelengths of the visible spectrum. And it's also the highest frequency. Remember, these are always supposed to be opposite or inverses of each other. So longest and lowest, shortest and highest. Okay. Visible spectrum, Roy G. Biv. Red, orange, yellow, green, blue, indigo, and violet. Red's the longest, lowest frequency. Violet's the shortest, highest frequency. All right. So our atomic emission spectrum, what does this actually mean? These are a series of lines. Please don't write all of this, okay? These are a series of lines of colored light produced by passing the light. Okay, I can go back. That's cool. Sorry. There we go. So remember, spectrum is really just colors when white light are separated in a prism. Colors when white light is separated in a prism. Those colors will separate into the order of Roy G. Biv, with red being the longest and lowest, and violet being the shortest and highest. Remember, you can abbreviate wavelength as a lambda, frequency as an F. No problem. All right. So the atomic emission spectrum. Okay, what really happens is this is a series of lines of colored light that get produced by passing the light emitted by excited atoms through a prism. And this can actually be used to identify elements. Okay, so really what it is think about this. If we have a tube of hydrogen and we add energy to it, it will actually glow. Okay, the tube of hydrogen will. Okay, kind of like a fluorescent light. That's the way to think about it, like a neon light. Okay, so if I have a tube and it's filled with hydrogen, and I add energy so that that glows, when I pass the light that comes from that through a prism, it'll actually just make these lines. Okay, it'll just make, and if I do it with helium, it'll just make these lines. If I do it with white light from the sun, then it'll make these lines. So this is just a way to identify elements because of how their light separates. Okay, so because of how their light separates when it's passed through a prism, we end up with what's called the atomic emission spectrum. So by how the light separates when it's passed through a prism, we can identify the element. All right. So by how the light passes through a prism, we can identify an element. Okay. So, all right. So talking a little bit just about the atomic emission spectrum for hydrogen. So here's the tube that I said contained hydrogen. And if we give it energy, it's going to glow. And when we take that glowing light and we pass it through a prism, it will separate into a band of purple or violet, a band of blue, a band of green, and a band of orangish color. Okay. It'll be an orange red actually. So those are the only 4 bands that will really show up. And they actually look like this. Okay. They look like what we have right here at the top. So I have these 4 bands are all that will show up. If I exchanged this particular tube right here and I exchanged it with mercury and I did the same thing, I would get 1, 2, 3, 4, 5, 6, 7, 8, 9, maybe 9 bands of light that would show up on this screen instead. So again, like I said, it's just really as the light goes through the prism, how it will separate. Okay, it really does represent the electrons changing energy levels. I will tell you that. So as the electrons drop down, they will jump out and then they'll drop back down, and that's what creates these different colors. Okay. So now quanta. Quanta is a vocabulary word I want you to write down. And quanta is a unit of energy. Okay, it's really a unit of light energy. Quanta was studied by the scientist Max Planck. And Max Planck found these energy parts. He just called them discrete units of quanta. So he found that energy was either absorbed or emitted. So he did experiments with atoms that dealt with the quanta energy. So Max Planck did experiments with energy being emitted or absorbed and called it quanta. The second part, I don't really want you to worry about right this moment, but what's going to end up happening is he created a formula, and that's going to be our second formula that actually determined the exact amount of energy because of the formula that we're going to talk about. Okay. So he did experiments which found energy that was emitted or absorbed, and he called it quanta. He then figured out a way for us to calculate that energy. So quanta is a unit of energy, and Max Planck did experiments that found that energy was emitted or absorbed and called it quanta. He also determined a way to calculate it. Quanta is a unit of energy. Max Planck's the scientist that did experiments about the energy being emitted or absorbed, and he called it quanta, and he came up with a way to calculate it. Okay. Now, the photoelectric effect was actually studied by Einstein. So I want you to write the photoelectric effect. And it was studied by Einstein and Max Planck. Okay. And Einstein really figured out that if you shined light, okay, on metal, it would cause electrons to flow, which would be a current. So it would cause a circuit to work. Didn't matter about the intensity that you shined the light on the metal. It only mattered about the frequency. This told him that light must not be just waves, but maybe particles instead. So the photoelectric effect really led us to believe that light had what we call duality. Okay. So that's what I really want you to write about the photoelectric effect. The photoelectric effect led us to believe that light had duality and wasn't just a wave, but also could be a particle. The particles of light were called photons. Okay. So Einstein studied the photoelectric effect with Max Planck. Okay, Max Planck went on with Einstein's study. But it led us to believe that, again, light is not just a wave, but also could be a particle. Those particles of light he called photons. And it led us to believe the information we have nowadays about light having duality, meaning that in some ways it seems to act like a wave, but in some ways it acts like a particle. When it acts like a particle, it's called photon. Okay. Again, don't write all of this because we're going to talk a little bit more about it on the next screen. So photoelectric effect led us to believe about duality. Okay. Okay. So going into a little bit more information about the photoelectric effect. Okay. Electrons called photoelectrons are ejected by metals. Okay. When light, again, shines on them. So really about the photoelectric effect, I want you to think about it as this. Light shines on metal. Metal ejects electrons. And those electrons create a circuit. The best way for me to think about for you guys to think about the photoelectric effect is y'all's solar powered cell phone power banks. Those ones that y'all sit in the room and literally as long as they're like shining, like light shining on them, they will charge your phone because they're like absorbing energy. Okay. That is the photoelectric effect. That's called a photoelectric cell. Okay. That you are having there in your cell phone bank charger. Okay. I know. No. Did it go away now? I know. I don't know what I need to do. Let me stop my share and I'll reshare it. We'll see if this will work. Yeah. That should be better, yes? I don't know why it shows up. It shows up every once in a while. Yes. Okay, cool. Sorry, I was like I didn't know whether y'all were seeing it or not. Okay. So like I said, the photoelectric effect is really like a photo cell. Okay. Light shines on it. Electrons shines on the metal that's in the photoelectric cell. The metal ejects electrons, especially alkali metals work really well. Okay. And then that those ejected electrons become a circuit or a current that's in a circuit. So really, photoelectric cells convert light energy into electrical energy. And like I said, the easiest way for me to give you that example is with those cell phone banks. Okay. But also like opening doors with photoelectric cells or security systems. A lot of them have a solar cell. Okay. But all solar cells are really just photoelectric cells because they're taking light energy and converting it into electrical energy. Now, I will tell you, red light doesn't work, but in the classroom, we have white light. And so that's why it'll work in the classroom or with sunlight or anything like that. But if you just shine red light on them, it won't actually work. So, is everybody good with the photoelectric effect? Shining light on metal Metal ejects electrons. Those electrons create a current, and a current provides electrical energy. Okay. All right. So here's our second formula of this part. All right. And that is E equals HF. Now, this is the one that I will remind you on your homework and on your classwork, it'll actually say E equals HV instead. Okay. But E stands for energy, and it will be in the units of joules. Okay. Let me draw real quick. And then the joules are just a J, capital J. All right. F will equal frequency, which, if you remember, is a hertz, or is the units of hertz, or it's units of seconds to the -1, or it's the units of 1 over a second. Okay. And then Planck's constant is a lot like our, speed of light constant. It's a number that I'm going to give you. Okay, it's on the papers, the classwork and the homework. It'll be on the test as well, but it's a constant that's always the same, and that is 6.63 times 10 to the -34th joule seconds. So those are multiplied together. All right. And typically when we multiply the hertz and the seconds right here in this unit will cancel out, and that's why we end up in joules. Okay. Other ways to write this equation, we could be solving for F instead. And if we solve for F, we could do E divided by H. Okay. And then I will tell you, I could even say, if we could solve for the frequency, then I could ask you to solve for the wavelength as well of the light by going back to our first equation and saying C divided by F. Okay. So you could take this F once you solved for it, plug it in down here and ask for the wavelength. So I might be able to give you the energy of something and ask for its wavelength just by using the two equations together. So just an FYI. Okay. Again, E equals HF. This is to find the energy of a photon. Remember, a photon is really just a packet of light energy. You can think about it like a Tide Pod, but the Tide Pod actually just, instead of having the liquid soap in it, it would have the light energy in it. That's what a photon is. Okay. And then the frequency and Planck's constant. Frequency is in hertz, energy is in joules, and Planck's constant is in joule seconds. All right. So let's calculate the energy of an individual photon. On yellow light, having a frequency of 2.73 times 10 to the 16th seconds to the -1. That could also say hertz, just to let you know. All right. So again, we're using yellow light. So its frequency is 2.73 times 10 to the 16th hertz. And this again has 3 significant digits, so my answer is going to have 3. All right. Your H value, and this actually should have been changed. I forgot to change it. It should be 6.63 because we don't take it to this many digits. So 6.63 times 10 to the -34th joule seconds would be Planck's constant. And we're looking for the energy. Okay. So again, if we were going to circle and underline things, we would circle the energy and we would underline the frequency because that's what was given to us. And we're trying to find the energy. All right. So for my energy equals H times F. Again, you'll see it as H times V on our papers. So we'd have 6.63 times 10 to the -34th and 2.73 times 10 to the 16th. Those of you that are sleeping, wake up and grab your calculator. Let's type. If your neighbor has got their head down, tap them, please. So 6.63, grab your handy dandy calculator. 6.63, then hit the EE button, negative 34, multiplied by 2.73, hit the EE button, 16, and then hit enter. And you should get 1.80999 e to the negative 17. If you got that answer, good job. Okay. We've got to round it to only 3 significant digits, though. So that will round to, you'll look at the 0.809. So that will round that to 0.81. So we will have 1.81 times 10 to the negative 17th. And that will be in joules because we're looking for energy. All right. Hopefully everybody got that calculation. All right. Now, with that, that's the last slide. Okay. We did an example of each type of the calculations for this section. I gave you some more vocabulary words about amplitude, wavelength, frequency, the photoelectric effect, a photon, a quanta. We talked about Max Planck as a scientist. We talked about the order of the electromagnetic spectrum. We talked about how the speed is the same for all of them. So as the frequency goes up, the wavelength has to go down. We talked about the order of the visible spectrum specifically, and we talked about the atomic emission spectrum. I am going to post this recording as well on the Google Classroom for you guys. So if you need to go back at any time and listen to it again, you can. All right. But right now, what I want you to do, it is 8:05. And you guys get out of class in 50 minutes. All right. So what I want you to do right now is I want you to work on your classwork, and I want you to make sure you've completed all 4 parts of it. So you've completed the first page, which was about periodic table review. You've completed the periodic trends. You've completed the electron configurations, and now you complete the EMS calculations. Then I want you to work on your homework, which means you're going to have quite a bit of time here to get things done, because I think most of y'all had finished 1 through 3, as well as part 1 and 2 of your homework. Now you're ready to complete part 3 of your homework, which would mean your classwork, which is not due until Wednesday, should be completely done in the time you're going to have in class today. Your homework should really get done in class today, okay, as well. And then if you guys still have time and you get all of that done, I am going to say that you guys there's an additional classwork worksheet that you guys should be able to work on as well. And if you are done, once you finish those 2, you need to ask Ms. Gooch for it. And it is the EMS calculations, or the atomic spectrum worksheet. Okay, so she has that as well. That is only to be worked on in class, though. So if you don't get it finished in class today, you'll have time next class to do it. But I don't want you guys to not be working on anything. Okay, so you have classwork to finish first, then homework to finish, and then your classwork on the atomic spectrum. Okay, so those are the 3 things that you should be working on for the rest of the class period. All right. If you guys have questions, feel free to send me a remind message, okay, or to email me, and we can get together and chat. Okay. Have a good one. Be safe. Hope to see you soon. Bye.